Are we going? Are we recording? Yes. Okay. There may be a little glare on the screen, but I have to leave the lights on so they can see you guys. Where's the camera? Right here. Hi.
Hi.
Okay, there we are. Can you see everybody for the most part?
Hi.
Hi. All right, so this is my last class. This is my 7th hour class, and we have a few other people joining us who aren't necessarily on screen. I couldn't fit everybody in. So, can you hear us okay?
Yeah. Good.
Okay, awesome. All right, so I know they've been looking forward to this, and I've been really excited about it. And they may have some questions as we go, so kind of like 5th hour. They may pop in and ask some questions. I might be asking for some of them, but we'll just kind of go from there. Okay, you guys ready? Yeah. All right.
Okay. Well, we didn't talk very much about where we're going to start, so I might start with a question that I'm not sure which group. Oh, yeah, we should. Thank you. This is Donald Lee Brown. He is a graduate student here at the University of Kansas, and I'll let him meet.
Hi.
Hello.
Mr. Barbara Anthony Torok, and she's a professor here in the physics department at the University of Kansas.
Yep. Yeah, there's about 26 faculty, and 4 of us are astronomers, and we got people doing all kinds of cool stuff. So, and we have lots of grad students. We have about 100 grad students. Many of them here, some from elsewhere. And we all talk about physics a lot. Some of us talk about physics that we learn from the sky and stars and planets more than others. So, one of the questions that I read from things you prepared yesterday, I addressed a little bit in the previous hour today, but it was a question that said, if Earth is turning really fast, why don't we notice it? And I said then, and I'll say again, that was a great question, and one that people asked Nicholas Copernicus in 1543. Copernicus wrote this book that was really, really, really groundbreaking. It was revolutionary, and that was the name of the book too. In it, he suggested that Earth is orbiting the sun, not the other way around. And in order to make that work, Earth also has to turn, and that's how we get day and night. And at the time, people said, oh, no, that doesn't make any sense. That isn't what I feel like. I don't feel us moving. I don't feel any sense of speed if Earth is turning on its axis, as it must, pretty fast. And he said, well, that's reasonable. I don't think you'd feel any sense of speed. And I want to help you understand what he was saying too. How many of you have ever been in a car, gone down the interstate at 60 or 70, or in Kansas, 75 miles per hour? How many of you have ever been in a car on the interstate going fast like that? Probably all of you. Did you feel like you were going fast?
Yes.
What makes you feel you're going fast? Seeing stuff go by? If you are in the car going really, really fast and you throw something up in the air, does it end up half a mile behind you? Does it? Unless you open the window. That would be wrong. If you just throw it, it'll land in your lap. Same as it would if you weren't moving at all. And the reason that's true is that you're all moving at that speed. So you're not aware of speed unless you look out of the car. If the car had the windows blacked up, it would be hard for you to tell. And Copernicus never had the experience of traveling that fast, but he'd been on ships and things, and he said, no, there's no problem here. If we're all moving at the same speed, we won't have any sensation or awareness of moving really fast. So he said, no, not a problem. So we can still go on thinking about Earth spinning on its axis. And of course, we're absolutely certain that that's a better way to think about what Earth is doing. So I'll let Donald pick up on one or something else.
Sure. So another good question that people had was, why does the moon look really big sometimes when it's rising, and then looks like it gets smaller? So I'm sure many of you have seen this, where you go outside at night and the moon is coming up and it's just coming up over the trees, and the moon looks extremely big. How many of you have seen this effect? Pretty much everybody, myself included, trip our
Yeah, cool.
Yeah, and then you go out a little bit later maybe, and not me, because it's past my bedtime, but you go out a little bit later and the moon looks smaller. It's higher in the sky and it looks a lot smaller. And this is actually there's two things going on. One of them being that, in fact, we do get closer and farther from the moon. Just the way the moon orbits the Earth, the orbit isn't perfectly, the moon isn't always the same distance from us. But the big reason why it looks like the moon is bigger, especially when it's closer to the horizon, is that it's sort of an optical illusion. The moon isn't actually getting bigger, of course. The moon is the same size, and the best way to test this for yourself is to turn into a little scientist and sort of either take a piece of paper and cut it so that it's exactly the same size as the moon when you see it, or to hold out your fist, and your fist is about the same size as the moon. So if you hold out your fist when the moon is close to the horizon, it should just about cover the moon. And if you wait a little while, and the moon gets higher in the sky, if you hold out your fist again and cover the moon, you'll see that your fist exactly covers the moon again. And what this indicates is that the moon actually isn't changing in size, because your fist isn't going to change in size, of course. And so the moon isn't changing in size. So what this tells us is this is actually sort of our mind playing a trick on us, and that in reality the moon is not getting closer or farther away or bigger or smaller.
Your brain does a job all the time, and it's kind of hardwired. It's like an app that's always running. It sees something and it kind of knows what it is based on thinking about how big it is or how far away it is. So I did this before, and it was kind of terrifying for everybody. If I do this, how many of you think my head got bigger? It feels bigger, like exploding.
Like the size of her head changed as she got closer.
Probably not. But you see, I look bigger, but it's because I got closer to the camera. So part of what Donald said is the moon is closer sometimes than others, so it does look a little bit bigger. But brain thinks when it sees the moon up in the sky, I've seen that before. It's the moon, it's about the same size as the sun, but it's a little confused when it sees it on the horizon. So it isn't real sure. And you may think, oh gosh, it's really big. You look away and you look back and it looks fine. So even when you know that, you'll probably see that again in your life. That's just a cool part of the way your brain and your eyes work together.
Hey Barbara, on that same topic, about how the moon looks bigger, like when it sometimes is close to the horizon and then gets smaller. How come sometimes when it's bigger or closer to the horizon, it also looks yellow or orange, and then as it goes up, it changes to white?
Right. The sun does pretty much the same thing. We see the sun when it's near the horizon, it looks oranger or redder, and especially if there's dust or smoke in the air, it can look really, really red. So the reason it looks maybe a certain color when it's low on the horizon is we're looking through a lot of air that has stuff in it. And stuff in the air scatters different kinds of light, different colors of light by different amounts. So generally when we look at something through a lot of atmosphere or a very smoky atmosphere, we see it look redder. Used to be when I was littler, there were a lot more fires in the autumn, and you'd see really red sunsets and red full moons too, but not so much anymore. We don't do so much burning. Well, one of the other questions that people have written was a big one. In fact, I think a couple people asked the same thing. How do we know how far away things are? That is a big, big, big deal in astronomy because we don't actually go anywhere. Except for people going to the moon and sending spacecraft to some of the planets in the solar system. For the most part, we just look, and we have to figure out what we're seeing by looking. And that makes it challenging. There's one way that we can get the distances to a few things, and it's about the moon again. So when the Apollo missions were in operation, astronauts landed in the moon way before you were born, and left stuff there, including some little mirror reflector things. Every day as the moon is up, astronomers at observatories fire a laser at the moon, and it reflects off those little mirrors. And you think, well, okay, how's that going to give me the distance? Well, we know exactly how fast light travels. So we just start a stopwatch. It has to be a really good one, because light travels really fast. It's only a fraction of a second or so. But the light goes to the moon, and it comes back, and by counting how long that takes, we have just measured the distance to the moon really, really, really well. We can do that to Venus and Mars also. So those things we've measured. Everything else, we have to figure out how much farther other things are by using geometry, and later on we use a little bit more physics. But the Hubble Space Telescope hasn't gone to visit any of those beautiful places. It's orbiting around Earth and has been for 25 years. So we have to get all those distances by thinking, not by measuring. There you go. Mars again?
I think another question that I'm seeing a lot on here is not so much about space, but more about you guys and kind of what got you into wanting to be a professor or get your graduate degree in this stuff. So what kind of inspired you to do what you're doing right now?
Yeah, I can go with my story. Well, so I'm a second-year graduate student, which means that I've gotten my undergraduate degree at a college, and before that I went to high school. I didn't actually do much astronomy before I got to college, and so during my freshman year at college, I had a physics professor who asked if I would like to, talk about what he did, and I said, sure, why not? Because he was my professor, so I wanted to make him happy. And so we had a meeting, and he explained that he used telescopes on top of the science building to measure stars that actually expand and contract. So these are stars that are actually getting larger and smaller, and so they look brighter and fainter to us over time. And that sounded very interesting to me. And so I said, okay, I'm interested. And after that, it was pretty much it just happened. At that point, I found everything really interesting. I got to learn how to use telescopes, and I got to go to conferences and meet other astronomers and talk to them. This is how I met Barbara at a conference. And so I just find what you can do in astronomy is really, really interesting, because it's really challenging in some ways, because all you can do really is look at essentially pictures of stars and other objects. And the challenge is to, just from these pictures, is to figure out what exactly these objects are doing. And so that for me is one of the really interesting things about being in astronomy. And so here I am, 6 years later, still doing the same thing. And eventually my goal is to be something like what Barbara does, to be a professor and do research and teach.
My story is too far back. I was a child of the space age, and I thought, well, that's really cool. But there was not astronomy being taught in high schools, not even in college. I studied physics in college. And then I had to convince everybody, my parents and teachers, Well, yeah, this is fine, but I really want to study stars, so I got some things to study stars. I had a telescope, a really dinky one when I was a kid, but you know, you figure out what you like, what you're good at, what you can do well, what maybe you'll be proud of, and anything that fits most of those things is a good thing to pursue. So, who knows what it'll be? You probably haven't seen it yet, but I hope you do.
Let's see. One of the other questions I'm seeing a lot on our little back channel thing that we have going is about breathing in outer space, like how do they breathe, and kind of like Fifth Hour we talked about the air and how there's not enough air for sound to travel. So you can kind of speak to those two things. That would be great.
Okay. I got a little distortion on that, but it sounded like breathing in outer space and
Yes.
sound transmission,
Yes.
stuff like that.
Yep.
No and no. There's not enough air once you leave probably more than 15 miles above where you are now to breathe. So you got to take it with you. So when people are inside a spacecraft, there's oxygen and air inside there, and they can breathe that. Once they leave the spacecraft, sometimes they have to go outside. They have to take air tanks. And air isn't just about breathing; it also helps you stay cool. So space suits have to help people stay cool. If there isn't any air, and that's true outside the spacecraft, then you can't have sound waves. Sound needs air to push and decompress through. So your ear hears sound because some pushing and decompressing in the air is making your eardrum vibrate. And that's what you interpret as sound. None of that's going to happen in space because there isn't enough air. So they have to use radios to talk to each other, but once they're inside the spacecraft, there's enough air for them to talk to each other. Did that cover most of what you wanted?
Okay, let's see. What else is on our list?
Aliens.
Aliens. Okay, they are driving me crazy.
Aliens are not real.
Okay, stop shouting.
Have you ever met one?
All right.
We're going to have one of you repeat the question.
Aliens.
Have you found any other sign of life on planets? Any other planets?
Like
Anything
aliens.
No.
No.
Okay.
What do you think?
Yes.
Yes.
No.
No.
Aliens are
No.
not real.
They're not real.
She shook her head yes. I thought she meant.
Well, let's straighten it up a little bit. Aliens, most of what we think of in aliens, it's science fiction, it's cool. No, we haven't found anything like that. We haven't found anything at all yet.
Yeah.
And the place we're looking hardest and are still hopeful
Mars.
is Mars. But if there was ever any life on Mars, it would be like bacteria, probably, and not recently. So we're looking for evidence that maybe there was life there at some time. I don't think very many people think there is life still. But the more we study how planets form, how atmospheres and oceans form, the more we see, wow, life is a really probable outcome of the way the universe is set up. So most astronomers think there's lots and lots of possibilities for life on different places, but we have no direct evidence of life anywhere other than on Earth at this time. But by the time you're my age, I think maybe we will. That's amazing. That's something you can look forward to and watch for.
Couple more questions. One of them is my own. So, like, when you were talking about bacteria, like, if we think the life on Mars could have been bacteria, how are you going to find evidence of bacteria when they can't be fossilized? Like, what sorts of evidence do you look for?
It's not necessarily fossilized. It might be frozen.
Okay.
So there might be the kind of material that you'd expect cells to be made out of frozen. And what more can I say about this?
Well, one of the things that people are looking for right now as evidence that perhaps that at least conditions for life could have existed in such a way that it was very probable that life existed, is that we look for the sort of the building blocks of life, so sort of the molecules that we know that on Earth are sort of associated with life, or that we think sort of can act as sort of the components of sort of the bacteria. So the molecules and the atoms or chemical signatures really that are present in life that we see on Earth.
It's kind of like collecting evidence that you call circumstantial evidence in a courtroom. Not like we saw somebody shoot the gun and commit the crime, but maybe we find a residue on their hand, or we find fingerprints on the gun. We're looking for fingerprints, and the fingerprints might be chemicals that life causes to be in the environment. So the Mars rovers are looking for chemical evidence of past life, and I think there's a chance they'll find it in the next few years, but it may be a long time, it may be never, we don't know. But we think it's there. The fact that we haven't found it doesn't mean it's not there.
And then I'm seeing some other questions. I showed them, like with the gyroscope, I showed them the radio telescopes. And could you guys talk about how those actually work? Because I know that's something we did not really talk about. And I'm seeing a lot of questions on that, like how do they know how far away some of these other planets are? How do the telescopes work that they use? Like the Hubble, how does that work? How does the radio telescope work? Can you guys speak to that?
We talk about radio telescopes, and then I'll talk about radio telescopes.
So when we talk about telescopes, really what we're talking about is we're talking about sort of these devices that we make, these contraptions that measure light. And so for telescopes like the Hubble, what we're measuring mostly is the light that our eyes can see. And so we're measuring what we think of as blue light or green light or red light. And so the way that works is we have a big lens, basically, and that lens collects a bunch of light and focuses onto a camera. Just as the way that many of you, I'm sure, have used digital cameras. The concept of an optical telescope is basically the same thing. We have a lens, and we basically press the shutter button, and it collects light, and that light is what actually forms the picture we see. Now, Barbara will talk about radio telescopes, but what I'll say is that radio telescopes are basically the same thing. They just measure a different kind of light called radio.
Yep. We actually sometimes call telescopes light buckets. You can see a lot of light, but your eye's only so big. If you had a bigger eye, you could collect more light. So we make telescopes bigger and bigger and bigger to make our light buckets bigger and bigger. So we collect more light by making telescopes bigger. And they work just like mirrors do, but if you curve a mirror, you can kind of recollect all the light on a camera or a detector. So radio telescopes do the same thing, but radio light is a little different. Our eyes don't see it. It has a different color, if you want to think of it that way. It's a really different wavelength. And we are not able to see that with our eyes at all. But it's light, and we can collect that kind of light, and then we can use electronics to convert it into a sound signal. And if you think that sounds really strange, how many of you have ever listened to a radio station?
What?
No, all of you.
Yeah.
So you have a thing that you call a radio, and that thing is actually taking the light waves that are broadcast by the radio station and converting them into a sound signal. It's not like the radio station is broadcasting a sound signal, because if it were, everybody would hear it all the time. You couldn't turn it on or turn it off or tune into a channel that you want to listen to. So they use different kinds of light signals. That's why they have different numbers on the dial. Those are the frequencies or wavelengths of the radio station's broadcast. And then your radio, what we call a radio, converts that to sound. So radio telescopes collect that kind of light, and sometimes if they feel like it, they convert it to a sound signal. So some kinds of things just kind of go, and then some kinds of objects go, dip, 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 dip. And we then think, oh, why is it doing that? And then we go off onto a rabbit hole of our own making. So telescopes work kind of like mirrors, but we try to shape them so that we can collect and then focus a lot of light.
I think a couple of them have some questions that they would like to ask. They're getting tired of me asking them for them.
Okay.
Make sure you guys speak clearly. You don't need to yell at them, but make sure you're speaking clearly. Okay, so, and also guys, please make sure they're like, okay. Alright, Cameron, go ahead.
Okay, so my question is if you can't breathe in outer space, then how can you breathe on Earth?
Alright,
No, she didn't answer.
okay.
So I heard if you can't breathe in outer space, how can you breathe on Earth?
Yeah, because I mean, Earth is in outer space, right?
It is. But,
It's earthquakes, so you should worry about yourself. Thank you.
so what we have here, the surface of Earth that we have less and less of, farther away we get from the surface, is atmosphere. And you got more of it right there than you would have if you went up a really tall building or a really high mountain. So it's being held by Earth gravity too. That's why we have more of it here than you'd have at the top of Mount Everest. By the time you get 10, 20, 15 miles up, there's very little air. And leave the surface of Earth by 100 miles or something, and there's practically no air.
Okay, let's just keep going around. Carmen?
Oh, yeah.
Okay.
What's your guys' own opinion on life being on other planets? Like, do you think
I think we need a relay.
A repeat of
Okay,
that.
she wants to know, like, what is your opinion of if there's life on other planets? Maybe not necessarily your scientific, like your politically correct opinion, but like, what do you really think?
Life on other planets?
Yes.
Well, what I will say is that in the past 10 years or so, very recently in fact, we've found thousands and thousands of planets around other stars. Now, for life to exist on those planets as we know it, so by that I mean life like what we see around us on Earth, that means that those planets have to be somewhat like Earth. And what we found is we found that, well, we haven't found too many planets that could be quite like Earth yet. But what studies have shown, if you can look at the number of planets around a certain number of stars, you can actually figure out how many planets probably exist in the entire galaxy. And what we've come to realize is that there are just an unimaginably large number of planets in this galaxy, just in this galaxy, to say nothing about every other galaxy in the universe. And so as Barbara mentioned earlier, a lot of astronomers sort of seem to hold the opinion that it's probably pretty probable that there may be life in places other than Earth. Now, whether that life looks like, humans, whether it looks like plants, or it just is bacteria, or something that we're not even thinking about, that's a big question that we can't really answer right now scientifically, because we just don't have the evidence for it.
Well, here's the one thing that if that's true, it's neat to think about, but don't expect to be paying visits. It's really, really, really hard to travel the huge distances that separate stars. So it's neat to think about other civilizations, other people, other worlds, but we have to take care of the one we have on our own.
Okay, Josh?
When was the last time someone's been up on the moon, and is there going to be another time someone's going to go up on the moon?
Relay.
He wants to know when was the last time someone was on the moon, and if we have any plans to go back.
1972, I think, last manned mission. The United States currently does not have spacecraft to move people and heavy loads from Earth to space. We had to hitch ride on a Soviet spacecraft, Russian, sorry, to get to the space station. we're kind of in a holding pattern right now. There are no astronaut missions right now. So plans to go back, if we go back, it would have to be for a good reason, I think. And there are maybe good reasons to prepare to go to Mars or to use the moon to study the rest of the universe. It would be a really good place to do that.
Tyler?
Alright, how does Hubble scope or whatever it is have so much, that's what I said, Hubble scope have so much like gas in it, and how would it come back?
It hasn't gone anywhere.
Whoa,
Orbiting.
Okay, hold on. Whoa, relax. Whoa, calm down, guys.
Let me make sure we heard you. The Hubble Space Telescope is just orbiting Earth. It has been. It hasn't gone anywhere.
no, that one's going like really far.
That's the Voyager.
And Voyager, it's like a
Voyager? Okay. How can it keep going? There's not much to slow it down. So once it gets going, it's not going to slow down very much from here on out. And the fuel that it has, which there wasn't very much, it uses to change direction a little bit, not speed up or slow down.
how is it gonna come home? Like come back?
How does it go?
How is it gonna come back to Earth?
It's
It's not.
gonna come back.
It's never coming back.
So it can send. So what it sends, just like anything we put in space, really, is
Stop, Jackson.
images or data. So like the Hubble Space Telescope, for instance, sends back pictures. But in general, with the exception of people, which we try very hard to bring back, most things that we put into space, we don't ever try to bring back. And so we either launch them like the Voyagers, or just they're going to go out of the solar system and keep going for a very, very long time. Or satellites that we put up into orbit, what we actually do is we do something we call deorbiting them. And basically we send them back through the atmosphere in such a way that they either burn up in the atmosphere, they break up in the atmosphere and crash into the ocean, or some combination of both.
Chris?
What would people do on the moon? Like,
Top louder, Chris.
what would people do on the moon?
On the moon?
Yeah, like what is the point of going to the
Well, you can think of a lot of things that would be hard, like gardening and the thing that I can think of doing on the moon would be a great place to have a telescope because there's no atmosphere to deal with. You could observe all kinds of light 24/7. So as a base for science, it would be pretty cool. It would be good practice. I think a lot of people think of it as practice for figuring out how to go to Mars. But those are the kinds of uses.
Okay. Brandon?
How many telescopes on how many?
Okay, how many telescopes are there on Earth?
How many telescopes?
Like big
Oh.
scientific ones.
That's like
Big ones? Hundreds? Little ones? I mean, who knows? I mean, there's probably 100 telescopes within 50 miles of where you are right now.
Alright. Carson?
What was the theory of how the sun was made?
How the sun was made?
Yeah.
Transformation class.
Well, what we know about stars, how they form, is there are these clouds of gas, basically. Anywhere we can look around us in space actually and find these clouds of gas. And what happens is, as these clouds of gas they get sort of clumpier and clumpier. So as they cool off, the particles of the gas can get closer and closer together. And what you get is it's just gravity. After a while, gravity sort of pulls these clumps of gas even more and more tightly together. They get denser and denser, so there are lots of particles in a little tiny area. And eventually, what happens is the particles get so dense in the center of these little clumps of gas that's when you get the fusion starting in the star. So that's when the star actually starts smashing particles together in such a way that you produce a lot of energy, and that energy is produced as light. And then what happens is, after fusion starts, you have this tug of war basically between two things in the star. So you have this tug of war between the pressure caused by light going outwards, and then gravity pulling basically the star together. And so gravity is holding the star together, even as all this fusion in the center of the star, all this smashing of particles together, is releasing energy and trying to push the star apart.
Did that take a long time?
Well, it depends on what you call a long time. So, in our lifetimes, we're never going to be able to see a star, a cloud of gas collapse, turn into a star. But in terms of sort of the lifetime of the universe, so we're talking tens of billions of years, this process tends to happen very fast. So we're talking millions of years.
It's a big galaxy. In your lifetime, a few stars will be born. And we can see newborn stars, kind of young stars. We can see stars in a lot of those different stages. So although we can't see one of them go through that cycle, we can see lots of different stars at slightly different stages of being born and forming.
All right. Well, we are about out of time for class. So I will share the email that we set up. I'm going to share that with them for the questions that we didn't have a chance to answer. Since we have about a couple minutes before the bell is going to ring on us. But thank you so much for taking your time. I appreciate it.
We'll sign out.
Stop! Ladies and gentlemen. Okay, now, there are questions.
Don't tell me to read the Bible. She's getting mad.
Okay, stop it. This is exactly what I'm talking about, you guys. We are not going into this discussion. Okay? I'm not going to tell somebody that they need to go read the Bible to figure it out or things like that. We're not going there, you guys. Okay? Whoa! I need you to stack chairs, please.
Oh my gosh. Tiffany, you ready to go take a test? Stay for it. Chris, stop touching. Stop touching. Chris, stop touching. Stop. Guys, go to class. Chris, stop. Chris, y'all go to class. Be gone. Walk away. Really? Come on, Nathan. I'm not All right, go to class, guys.
I'm going. Miss David, stopped it for you.
So I should stop my screencast.
I'm going to class.